No nation which expects to be the leader of other nations can expect to stay behind in this race for space.
Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and thank you for your support on Patreon. We appreciate you. A lot of people are worried about rising atmospheric carbon dioxide levels, and we should be. While it is true that carbon dioxide levels naturally fluctuate, and the levels have been higher in the past than they are now, people weren't alive back then when they were higher, and these ancient increases led to a dramatic shift in the climate. At this point, there is no reasonable doubt that human activity, specifically the burning of fossil fuels and forest clearings, has outpaced the Earth's ability to adapt and absorb carbon dioxide. Within my lifetime, carbon dioxide levels have gone from 320 parts per million to just over 420 parts per million today. This has resulted in a warming of Earth's climate, and if it continues, there will be catastrophic damage to our crop yields along with extreme weather patterns and significant loss of land from sea level rise. That all being said, dealing with the problem has stirred up a lot of debate and government action, most of which has been worse than useless. While investments in wind and solar are now paying off, nuclear would be by far the best option. But since there is a lot of political opposition to it, many governments have invested heavily in hydrogen fuel technology, which, except for a few niche applications, has been a wasteful distraction. Producing enough hydrogen gas today to power our homes, businesses, and transportation would produce much more carbon dioxide than just burning the fossil fuels, unless you use solar or nuclear. But nuclear plants take decades to build, and the electricity from solar power is better used being put directly into a battery. It is not efficient to use solar-powered electrolysis to produce hydrogen, then compressing and cooling it to extreme pressures and temperatures for storage before converting it back into energy. We could instead store the hydrogen in power paste form, as pioneered by Fraunhoffer Gesellschaft, headquartered in Munich, Germany. Power paste, which contains magnesium hydride, can hold an amount of hydrogen equal by volume to a high-pressure cryogenic tank, while still at ambient pressures and temperatures, needing only hot water to liberate the hydrogen for use in a fuel cell. If we could find a cheap and efficient way to make hydrogen, this would probably be the perfect storage solution. But right now and for the next couple decades, we can't make cheap hydrogen. And while fossil fuels are undoubtedly contributing to global climate change, the solution is not to abruptly stop using them, because doing so would kill millions, if not billions, of people through famine, extreme temperatures, and collapse of our current civilization. Fossil fuels became so ubiquitous for a reason. They are fairly easily available and are very energy dense. Almost all of the world's infrastructure runs on fossil fuels. But is there any new technology becoming available now that could help ease this problem in the short term? Let's look to see if there's a better way. Modern internal hydrocarbon combustion engines are about 25 to 40% efficient at turning fuel into energy. Boosting that efficiency to 50 or even 60% would allow us to produce the same or even more energy while still reducing carbon dioxide emissions. And the technology to do this efficiently is just becoming available to us. The quest for efficient and sustainable energy sources has always been a driving force in human history. From fire to fossil fuels, we've sought ways to harness energy to power our world. In the late 19th century, the dawn of the electricity era sparked further interest in finding cleaner and more reliable energy solutions. Enter the fuel cell, an electrochemical device that converts the chemical energy of a fuel into electrical energy. The first fuel cells were invented in the early 1800s. Sir William Grove designed what he called a gas battery in 1839. But it wasn't until 1959, when a team of engineers at General Electric made them somewhat practical by designing a hydrogen oxygen fuel cell they called the Bacon cell, after its inventor Francis Thomas Bacon. not to be confused with the 19th century English philosopher. Tom Bacon was a British engineer who lived from 1904 until 1992. His breakthroughs in the 1950s led to the famous Apollo fuel cells in the 1960s, which made traveling to the moon possible. These were alkaline fuel cells and produced up to 2.3 kilowatts of power, generating about 28 volts and 55 amps steadily for 2 weeks. They operated about 80 degrees Celsius, or 176 degrees Fahrenheit. These high temperatures were necessary for their efficiency. There were 3 of these units on each command module, and 1 on each lunar excursion module. The oxygen tank for one of these fuel cells famously exploded during the Apollo 13 mission. These fuel cells had an efficiency of about 55%, while modern polymer electrolyte membrane fuel cells can now reach 60%. But these 2 types of fuel cells cannot tolerate any carbon contamination, like carbon dioxide or carbon monoxide gas. They must be fed pure hydrogen and oxygen to work, taking us back to the hydrogen production problem. And most fuel cells require very expensive platinum-based catalysts to allow them to work efficiently at even these temperatures. Molten carbonate fuel cells, on the other hand, can use almost any hydrocarbon and still operate at about 50% efficiency. Raising the temperature and adding modern thermovoltaic cells could boost that as high as 75%, more than doubling the current efficiency of our hydrocarbon infrastructure. Dr. Karl Kordesch, an Austrian scientist, played a pivotal role in the development of molten carbonate fuel cells. In the 1950s, he started investigating fuel cells using molten carbonates as electrolytes, pioneering their practical applications. His work paved the way for further advancements in this field, and there are molten carbonate fuel cells being used right now for energy production. So what sets the molten carbonate fuel cell apart? The molten carbonate fuel cell consists of several key components. At its core lies the electrolyte, a mixture of molten carbonates. This environment allows for efficient ion conductivity. On either side of the electrolyte, we find the electrodes. The anode, often made of nickel, allows the fuel to undergo oxidation, while the cathode, typically containing a porous material, facilitates the reduction reaction. The fuel, such as hydrogen or natural gas, is introduced at the anode, while the oxidant, usually air or oxygen, enters at the cathode. As the fuel and oxidant react, a chemical reaction occurs. The carbon dioxide produced at the anode combines with the carbonate ions in the electrolyte, forming more carbonates, generating an electric current that can be harnessed for various applications. Molten carbonate fuel cells offer several advantages. First, their high operating temperatures, 600 to 700 degrees Celsius usually, enhances their efficiency and reduces the need for precious metals as catalysts. Second, they have a lower sensitivity to carbon monoxide, enabling the use of a broader range of fuels. Lastly, the waste heat generated by these cells can be harnessed for cogeneration. Cogeneration, also called combined heat and power, is a process where a molten carbonate fuel cell system simultaneously generates electricity and utilizes the waste heat produced for other thermal applications, like those thermovoltaic cells we mentioned earlier. Beyond their efficiency and versatility, molten carbonate fuel cells play a crucial role in mitigating climate change. By using carbon-based fuels such as biogas or natural gas, these cells allow for the offsetting of greenhouse gas emissions from car engines and power stations. The materials used in molten carbonate fuel cells are carefully selected to withstand the harsh operating conditions. High-temperature alloys, ceramic electrolytes, and specialized catalysts are employed to ensure longevity and performance. The utility of molten carbonate fuel cells extends beyond our planet. In the realm of space exploration, these cells hold promise for producing reliable power in challenging environments. On Mars, where traditional energy sources are scarce, and solar power is reduced to less than half of what it is on Earth, molten carbonate fuel cells could become vital for sustaining human colonies. Liquid methane is much easier to store than liquid hydrogen, and can be produced through the Sabatier process on Mars, by combining hydrogen gas, electrolyzed from the water on Mars, with carbon dioxide taken from the Martian atmosphere. This produces fuel for the starships that will be landing on Mars, and when combined with the other product of water electrolysis, oxygen, produces effective reactants for our rovers. Rovers equipped with molten carbonate fuel cells could produce electricity for power and heat to keep the astronauts warm as they explore the surface. But molten carbonate fuel cells impose significant challenges on the materials from which they are constructed due to the extreme operating conditions they endure. MCFCs operate at high temperatures, again typically around 600 degrees Celsius or 1,112 degrees Fahrenheit, in the presence of corrosive molten carbonate electrolytes. These conditions can subject the materials to various forms of degradation, including thermal stress, chemical reactions, and corrosion. The molten carbonate electrolyte can react with metals, alloys, and ceramics, potentially leading to material loss, erosion, and degradation of efficiency over time. To withstand these harsh conditions, materials for MCFCs need to exhibit excellent high-temperature stability, corrosion resistance, mechanical strength, and long-term durability. Researchers and engineers are continuously exploring and developing advanced materials and coatings that can withstand the demanding environment of MCFCs. Catalysts also play a crucial role in the operation of molten carbonate fuel cells, facilitating the electrochemical reactions that occur at the fuel cell electrodes. MCFCs typically employ catalysts to enhance the kinetics of the oxygen reduction reaction at the cathode and the fuel oxidation reaction at the anode. These catalysts can significantly influence the overall performance and efficiency of the MCFC. Platinum and palladium, called noble metals because they don't react much to other metals, are commonly used as catalysts due to their excellent electrochemical properties. However, the high cost and limited availability of these noble metals poses challenges for widespread commercial adoption. To overcome these limitations, researchers have been exploring with alternative catalyst materials and composite structures to improve the catalytic activity, reduce costs, and enhance the durability of MCFC catalysts.
Carbon cash. Even as energy suppliers continue to rely more on wind and solar power, increases in energy demand will require diverse portfolios that include coal and biomass. Researchers at Idaho National Laboratory can now turn such carbon sources directly into electricity without producing many of the pollutants associated with burning fossil fuels or biomass in a power plant. Direct carbon fuel cells turn finely ground carbon directly into electricity via an electrochemical reaction. The concept is similar to hydrogen fuel cells that power everything from cars to rockets. But unlike hydrogen, which takes a lot of energy to produce, the fuel for direct carbon fuel cells comes directly from biomass or coal. Now, the carbon cache represents a new generation of direct carbon fuel cell. First, the inventors developed an anode made of woven ceramic that is both hollow and porous. This design allows more carbon fuel to contact the anode, increasing the reaction's efficiency. Second, they devised a carbon carbonate fuel that flows better at lower temperatures than carbon alone. The improved fuel enhances contact with the anode, further improving the cell's efficiency. In the end, carbon cache's peak power density is 6 times higher than existing DCFCs at higher temperatures. Since it produces nearly pure CO2 without other pollutants, carbon capture technologies are easier to implement. Carbon cache could make electricity generation from resources such as coal and biomass cleaner and more efficient. The technology has drawn the attention of companies in the US and Canada that wish to explore the fuel cell's potential for commercial-scale electricity generation.
These advancements in catalyst technology aim to maximize the efficiency and cost-effectiveness of MCFCs, making them a more viable and sustainable option for clean energy generation. The higher temperatures of molten carbonate fuel cells may be hard on the materials, but they have a positive impact on the efficiency of MCFCs. Here are some reasons why. MCFCs operate at elevated temperatures, typically again above 600 Celsius. These higher temperatures accelerate the reaction rates, leading to more efficient conversion of chemical energy into electricity, thus improving the overall fuel cell efficiency. The molten carbonate electrolyte used in MCFCs exhibits better ion conductivity at high temperatures. This improved ionic mobility allows for more efficient transport of carbonate ions between the electrodes, facilitating the electrochemical reactions and reducing internal resistance within the fuel cell. Lower resistance translates to less energy loss and improved overall efficiency. High temperature operation improves the thermodynamic efficiency of MCFCs. According to the Carnot efficiency limit, the maximum theoretical efficiency of a heat engine increases with higher operating temperatures. By operating at elevated temperatures, MCFCs can approach this thermodynamic limit, resulting in improved energy conversion and overall fuel cell efficiency. MCFCs generate substantial waste heat due to their high temperature operation. This waste heat can be harnessed and utilized for cogeneration purposes, such as the combined heat and power systems we spoke of earlier. By simultaneously producing electricity and capturing waste heat for heating or other industrial purposes, the overall efficiency of MCFCs can be significantly enhanced. But remember, the high temperature operation in MCFCs also presents very serious challenges on material durability, corrosion, and long-term stability. Most molten carbonate fuel cells utilize nickel-based alloys for their construction. The specific nickel-based chromium alloy commonly employed in MCFCs is Inconel, typically Inconel 601 or 625. Inconel alloys are highly resistant to the corrosive nature of the molten carbonate electrolyte, which is a crucial requirement for maintaining the integrity and longevity of MCFC components. These alloys can withstand the harsh operating conditions of MCFCs, including high temperatures and the presence of reactive carbonate ions. Additionally, Inconel alloys possess favorable mechanical properties, such as high tensile strength and good thermal stability, which are essential for supporting the structural integrity of MCFC components. These alloys exhibit dimensional stability under the thermal cycling experienced during startup, shutdown, and load cycling of the fuel cell. But while Inconel has been amazingly effective as a high-temperature corrosion-resistant material so far, even better alloys are being developed thanks to advanced technologies. One of these innovative alloys invented by NASA is GRX 810. This is a 3D printed alloy that fuses specific metals and specific patterns layer by layer. It has turned out to be twice as strong, over 1,000 times more durable, and twice as resistant to corrosion compared to the best older alloys. These unique properties could make it possible to run molten carbonate fuel cells at much higher temperatures, which could dramatically improve efficiency and increase cogeneration. Let's look closer at this amazing alloy and its advantages in the context of high-temperature fuel cells. GRX 810 is a part of NASA's Transformational Tools and Technologies project and is an oxide dispersion strengthened alloy. The project used intelligent thermodynamic modeling to predict an alloy's characteristics, then advanced 3D printing technology to produce it for testing. Alloys are composed of a combination of metals and have been used for thousands of years. The Bronze Age started when humans learned to melt and mix copper and tin, creating a much stronger and more durable metal. Steel is a mixture of iron and carbon, and stainless steel, discussed in this lesson, was discovered when researchers added chromium. Inconel was made by mixing mostly nickel and chromium. When molten elements are mixed, they spontaneously form certain patterns. The most common patterns formed are simple cubic, face-centered cubic, body-centered cubic, hexagonal closest packed, and cubic closest packed. What pattern the elements assume can affect the alloy in profound and complex ways, and small amounts of other elements can be added to coax the main elements into desired patterns. The two main types of steel are austenitic and martensitic. Austenitic steel is face-centered cubic, while martensitic steel is body-centered cubic. Austenitic stainless steels are primarily composed of iron, chromium, and nickel, with smaller amounts of other elements such as manganese and nitrogen. The most common austenitic stainless steel is 1818 stainless steel, which contains approximately 18% chromium and 8% nickel. The chemical formula for this alloy is typically represented as FeCrNi. Martensitic stainless steels have a higher carbon content compared to austenitic steels, which allows them to be hardened through heat treatment. They are primarily composed of iron, chromium, and carbon, with smaller amounts of other elements. The chemical formula for martensitic stainless steels is typically represented as FeCrC. By the way, the steel used by SpaceX to build its starships is called SX500 or SpaceX stainless steel. It is a type of martensitic steel with a unique mix of other elements, the exact formulation of which is a trade secret. But these additives make it more heat resistant while maintaining its strength at cryogenic temperatures. This mixing and production method worked well throughout the 20th century, giving us better and better alloys. But when 3D metal printing was developed, allowing us to make metal works of engineering art impossible by any other method, caused material scientists to start wondering about using this technology to put nanoscale particles of each element exactly where they wanted them. Now remember, nanoscale means dimensions on the order of 10 to the minus 9 meters, a billionth of a meter. This would allow us to think up a pattern that looks promising, with the help of computer systems for thermodynamic modeling, and then print a potentially useful alloy in just a few hours. The scientists discovered GRX 810 after just 30 simulations. The manufacturing process involves selectively melting and layering carefully placed nanoparticles of the specific metal powders, and using a laser or electron beam to fuse and create complex structures. Printing and testing the alloy confirmed its amazing properties. GRX 810 is an oxide dispersion strengthened alloy, also called ODS. This means it is a class of materials that combines a metal matrix with small and uniformly dispersed oxide particles. These particles are usually composed of yttrium oxide or titanium oxide, uniformly distributed within the metal matrix. The particles act as strengthening agents and effectively hinder dislocation movement, enhancing the alloy's strength and resistance to deformation, allowing these alloys to have excellent mechanical strength and creep resistance, thus preventing grain growth and maintaining strength even at high temperatures, making them perfect for high-temperature, high-stress environments, like rocket and jet engines, but also for high-temperature efficient molten carbonate fuel cells, especially because the presence of oxide particles in ODS alloys also enhances their resistance to corrosion and oxidation. The oxide particles act as barriers, hindering the diffusion of corrosive species and protecting the underlying metal matrix from degradation. Think of it like the layer of aluminum oxide, also known as sapphire, that forms over aluminum metal, making it more resistant to corrosion. Fuel cells often operate in corrosive environments due to the presence of the reactive gases and electrolytes. GRX 810 demonstrates remarkable corrosion resistance, allowing it to withstand the harsh conditions encountered in these fuel cells. ODS alloys are also known for their resistance to radiation damage. The dispersed oxide particles act as sinks for radiation-induced effects, such as dislocations and vacancies, effectively reducing their mobility and preventing the degradation of the alloy's mechanical properties under irradiation. This combination of high-temperature strength, corrosion resistance, and radiation resistance will make these alloys perfect for applications like advanced nuclear reactor components, gas turbine engines, heat exchangers, rocket engines, fuel cells, and high-temperature structural applications for aerospace and energy sectors. The invention of this amazing alloy could revolutionize our efficiency while reducing our impact on the environment. Imagine a battlefield ambulance made from a Cybertruck or Ford F-150, towing behind it an efficient hydrocarbon-fueled molten carbonate fuel cell generator. This system could efficiently use anything from liquid natural gas to potentially coal, allowing the vehicle to travel thousands of miles on the battlefield, saving lives. While this would be an amazing way to make our existing infrastructure more efficient, there are other applications to this technology. GRX 810 is also electrically conductive. The alloy's metallic matrix enables efficient electron transfer within the fuel cell, facilitating the generation and flow of electrical current. Electronics made from this material may solve our problem of making computers work on Venus. What is the future of this nanoscale variable material printing technology? How long will it be before we can print solid-state computers and other electronic devices on the picoscale, 10 to the minus 12 meters? A single carbon atom is about 20 picometers in diameter, while one of copper is about 135 picometers. Using advanced atomic printing technology, a civilization could make electronic components at the smallest possible scale, limited only by quantum tunneling effects and the uncertainty principle. A device made in this manner would be almost impossible to disassemble and analyze, and we would need to use gamma-ray lasers to scan the interior. As an interesting aside, if the unexplained aerial phenomena being talked about in the news, including the stories of recovered alien ships and beings, has any validity, and I am still skeptical, I'll make a few predictions. First, we did not shoot them down, and they didn't travel all the way from another star system just to fall asleep at the wheel and crash on arrival. There would have to be 2 or more species or 2 or more factions within one species that don't agree on how to deal with us. And they are shooting each other down. And I will make one more prediction. If we have recovered the technology of species capable of traversing the interstellar blackness, that technology is solid-state 3D printed on the atomic scale. And we are like ancient Egyptians with an iPad, brilliant in our own way, but limited by the current progress of our civilization. We might be able to operate it for a little while, at least until the battery runs down. But we would lack the tools needed to analyze and duplicate it, at least for quite a while. Something to think about. Thanks for listening, and stay safe. At Astra Pro Terra.
Carbon, originating from sources including coal and biomass, continues to be the dominant fuel source for power generation. However, the environmental impact of carbon dioxide emissions remains an issue. Direct carbon fuel cells, or DCFCs, offer a means to increase energy conversion efficiency and thus reduce the environmental impact. In their communication in advanced materials, Dong Ding, Ting He, and co-workers from Idaho National Laboratory in the United States fabricate an ultra-porous ceramic framework with 3D architecture as an anode for high-performance DCFCs below 600 degrees Celsius. A fabric textile coupon was immersed in a solution of a highly conductive cerium gadolinium oxide compound, or GDC, and nickel precursor, and then fired to form a nickel oxide GDC ceramic textile. The ceramic textile was punched to size and then bonded on the top of a GDC carbonate electrolyte using a nickel oxide binder suspension, followed by a co-firing process. A mixture of carbon and carbonate was loaded on the 3D anode frame before the fuel cell assembly. The as-prepared ceramic textile has sufficient mechanical strength and flexibility and can be readily applied to numerous electrochemical devices. Scanning electron microscopy of a calcined 3D anode framework revealed bundles of hollow nickel oxide GDC fibers knitted together. This porous structure allows penetration of carbon particles. Scanning transmission electron microscopy shows a uniform distribution of nickel and cerium elements, and electron energy loss spectroscopy shows peaks corresponding to oxygen, nickel, cerium, and gadolinium, indicating that the hollow fibers are composed of nickel oxide and GDC.
In this technology, the solid carbon can readily go through our 3D ultraporous electrode and reach the interface between electrolyte and electrode, realizing the direct electrochemical oxidation rather than gasification into carbon monoxide, which is the actual fuel for most direct carbon fuel cells.
A DCFC operating at 500, 550, and 600 degrees Celsius demonstrates excellent performance with maximum power densities of 143, 196, and 325 milliwatts per square centimeter, respectively. The 3D anode framework before loading the carbon fuel shows excellent contact between the hollow fibers and the GDC carbonate electrolyte. Addition of carbonate to the carbon fuel increases the carbon particle distribution throughout the hollow fibers during operation and extends the triple phase boundaries region, leading to improved performance.
We do believe that it will have a significant impact on our society when a variety of the fuels such as coal, coke, tar, biomass, and organic waste are used for efficient electricity generation with much less carbon footprint.
To find out more about this novel anode for direct carbon fuel cells, please visit the Advanced Materials homepage.